second floor. You just sit on the wall. It doesn't matter. When it's on the wall, it's right there. Like the guy on the queue.
Your camera so that you're not in my class. Okay, none of you actually make comments. No, I prefer it. Want to tell me something, just tell me. Two things, we're getting there. I'm going to take a look at the homework while we're practicing our quiz to make sure that you have everything you need so you can get it done and knock it out pretty quickly. But two more things that you need to know for today's quiz. The first is something called basis vectors. In two dimensions, there's an I and a J. I think that physics might use different notation because I is also the imaginary number I, which is not really imaginary. It's used in all kinds of mathematics, but you'll recognize it. So you said today's quiz. I know we're practicing today. Oh. You're having a little heart attack there. So these are specific vectors that are perpendicular to each other. You can actually prove they're perpendicular by taking the dot product and showing the dot product 0. Do I got your attention? All right. And when you graph them, this is what they look like. 0, 1 is right here. So this is the vector 1, 0. Sorry. This is I. And then J is this vector right here. This is J. Why these vectors are important is that we can take any vector that you have and represent it in terms of the basis vectors. The coefficients of these things will change. So for example, if I have 2, 3 like this, I can express this vector as 2 times I plus 3 times J. Give me 1 second, and you can give me an example. So I didn't really understand why these were important when I was taught them, and you might not either because I don't know how much of what I'm telling you comes through. But I learned later when I was programming things for a class called numerical analysis that representing things like this way really gives us a way to not think of vectors as just arbitrary infinite amount of vectors going through R2, for example, two-dimensional space. But instead, all I need is the coefficients, the 2 and the 3, and I have a representation with the I and the J. It's safe space when you're computing. That's what I've seen it used for. So I see it used all over. For example, microbiome data. Everybody's microbiome looks a little bit different. It just will, because everybody eats differently, everybody works out differently, we're all doing different stuff. We would expose to different chemicals. We're in the US. We're exposed to different chemicals. And so our microbiome all looks different. You can actually take, here's a real world example. You can take all the bacteria, gut bacteria that we know about, and then ask yourself if, let's say, we take Jacob's microbiome, and then we find out, well, he's got this bacteria, this amount of this bacteria, another amount of another bacteria, but most of them are zeros because not every bacteria is going to be covered. Then that would make a vector because you just have zeros for if he didn't have it, maybe a 2 for if he had twice as much, so forth, and you'd get this vector. And then really what you want to do is be able to work with vectors that are huge, lots of components to them, and compare them to other vectors. So what you want to know, for example, almost every day you see a new finding on the microbiome. You find something new, like you're supposed to eat. You guys know about this stuff? You're supposed to eat sauerkraut, yogurt. Those things are good for your microbiome. right? You're not old enough. You don't worry about these things yet. But people who eat differently, like for example, if you eat a cookie, some people don't respond poorly to that cookie because their gut microbiome is better off than someone else's gut microbiome. So usually people who have like poor gut microbiome data, they don't end up responding well to things. So that's an important area that we're looking at right now. We see something new almost every day because we're getting better and better at like analyzing that data or even collecting that data. So when you have huge data like that, you want to store it inside the computer. You don't want to store every single vector the same way. Only the coefficients are really important. And that's why you write it this way. So that's the why behind it. You can also have this 3 dimensions. So the right way to look at this is x, y is this way. That's not the way math does it. We always do it some strange way, but we do it like this. The elevator is the z. It's my 3-dimensional plot. And in this case, you would have I, j, and k. You would have this vector right here would be I. This vector right here would be j. Same as before, except now you have a third component. And the last vector coming out towards you is k. Like that. So again, this is the three-dimensional basis vectors. Those are the 2-dimensional ones. See if I covered everything that you need. I think I got it. All right, any questions on this? It's kind of weird that you're learning this, but you're learning this specifically because physics asks us to teach it this semester. There's not a connection to, well, there's kind of a connection to linear programming because you can express those things in terms of vectors and matrices. There's a connection there, but the real connection is that you have to actually do this next semester in paint. Physics and nuclear engineering, not PAIN. All right, any questions about this? So there's plenty of examples actually on that sheet that I gave you doing this, but some of you want to like actually do it in class. So hopefully it makes sense. Ready to try it out?
Yeah,